Okay, in the last lecture, I have in the notes itself, I have made one correction that if you choose epsilon is equals to u minus v itself, whenever u is greater than v, if you assume that means v is another upper bound, and you want to claim that u is least upper bound, but on the contrary, we have assumed that u is greater than v, then we defined epsilon is equals to u minus v. So then u minus v definitely strictly greater than 0, and then then v is equals to u minus epsilon, and you know that for every epsilon bigger than 0, u minus epsilon is not an upper bound. So then you can apply this condition. Okay, then what is this u minus epsilon is nothing but v. So v is no more an upper bound if you assume that u is greater than v. Okay, so that will be contradiction, and contradiction to the assumption that u is an upper bound such that u is greater than v. So there is no other possible upper bound which is lies left of u, you can say. Okay, right. So this claims establish our claim that u is a least upper bound whenever it satisfies the following condition. Okay, right. Thereafter, this was the the condition that in upper bound u of a non-empty set S in R is the supremum of S if and only for every epsilon there exists an S epsilon in S such that this happens. Okay, and then we have stated the completeness property of R. Okay, the name itself is complete, means like R is complete, but R is complete with respect to some other thing as well. Okay, when we will say a set is a space, so we will slowly maybe in the next semester course, or maybe in the linear algebra or other courses, you may learn that why we will say R is complete. Okay, so this completeness property is nothing but here is relating the supremum property, okay, which says that if you consider any non-empty subset of R which has upper bound, okay, so if you consider any non-empty subset of real line which has its upper bound, then its supremum exists, and then supremum is belongs to R. Okay, so S has upper bound means that doesn't mean that we are saying that S contains upper bound. Okay, S has an upper bound means that may be outside S, that may be inside S. So similarly, supremum S exists that may be inside S or may be outside. Okay, but if you that can be proven that if S contains an upper bound, suppose S is a non-empty subset of R and S contains its upper bound, then that upper bound itself becomes a supremum. Okay, that also can be proven. Similarly, you can write the infimum property of R, which says that if you take any non-empty subset of real number that has lower bound, it also has a infimum in R. Okay, so if you say S is an empty set, S is subset of R, S has lower bound, then its infimum is exist, and infimum of S is also in R. Okay, right. Okay, so with this property, so this property has a lot of applications. So the very first application is known as Archimedean property. Okay, and which is asked many times during your maybe interview as well. Okay, so sometime this is a very well known property, and which says that if X belongs to R, if you take any point on real line without any X in R, then you're always able to find a natural number sitting on the right of it. Okay, the Archimedean property says or establishes the proof. Okay, so this certainly assumes some of the axioms like well ordering property we have learned for the set of natural number, that if a set has if a subset of n is non-empty, then it has least element. Okay, that's a well ordering property, right? And just now we have learned the completeness property of R also. So we are going to use maybe both of them or maybe one of them. Okay. So now suppose if we want to establish this result, suppose if x belongs to R, so you fix x belongs to R, and let's say there does not exist any n. What will it give you? That then you will have then if not true, if the above thing is not true, if not true, then what happen is you will have then n is less than equals to x, or n is strictly less than x. You can say for all for all n belongs to set of natural numbers. Right? So this will implies n has an upper bound. N has an upper bound. Because you take any element of n, that will still lies on the left of this fx x for a given x. Okay, then it says that this x becomes an upper bound. So n has an upper bound. Also, n is non-empty. So n is a non-empty subset of real line which has an upper bound. So then supremum property, the completeness property of R. So completeness property.
Sir?
Yeah.
Sir, if not true, here you are trying to say that there does not exist any natural number.
Yes,
which
sitting on the right. Yes, which sitting on the left of right of it. Yeah.
Sir, but we would have the least greatest value of something, of any x.
Least greatest value of something means?
Like greatest integer we say.
Okay.
It's opposite. So least integer value, sorry. We would have no of x.
No, x is fixed, right?
Okay, we are fixing it.
X is fixed. Okay. X is fixed. Suppose you are able to find an x such that this does not true. Means that x is fixed now.
Okay.
For a given x, suppose this for this x, that this property does not hold. So x is fixed here.
So this is all hypothetical.
Yes. Okay. So completeness property of R gives what? So this gives you n has supremum in R. So let's let supremum of this set of natural number is u, which is not true. It's indeed which we are going to claim now. So let supremum of set of natural number is u. Okay, now, so when you have supremum of natural number, so u is a supremum. So then u minus 1 is not a supremum, means u minus 1 is not an upper bound. Because of previous result that u is a least upper bound if and only if for every epsilon bigger than 0 there exists an s epsilon in S such that u minus epsilon is strictly less than s epsilon. Okay, so 1 is greater than 0, u is not an upper bound of n because u is a least upper bound. So if you take slightly left of u, any number, that is no more an upper bound. Otherwise, if it is an upper bound, that it will become a list. That will not be a list. So that will give you the this answer to this is u minus 1 is not an upper bound. So what does that mean? So this implies, so this gives you, so this implies there exists some, you can say small k belongs to natural number such that u minus 1 is less than k right? Which is, so this implies u is less than k plus 1 and k is n, so k plus 1 is also in n, set of natural number. So this implies u is not an upper bound. Because you are able to identify a point in set of natural number which is sitting on the right of it. So u is no more an upper bound. So it's a contradiction to the fact that supremum of S is or supremum of n is u. So where is that? So u is no more an upper bound. So this means this does not mean it is not possible. So this will goes to contradiction that n has an upper bound. But this only leads when you have assumed that if not true. Okay, so what it gives you is our assumption was wrong. Our assumption was wrong. Means this implies for x in R, you will have there exist and you that will depend on x itself, and x belongs to set of natural number such that x is less than equals to nx. Now see, for x is strictly less than 0 or less than equals to 1, there is nothing to prove. So you can, without loss of generality, you can assume that x is strictly greater than 1, you can say. Okay, because set of natural number has its base element is 1. So Archimedean number sitting on the right, on the left of 1 will cover this x belongs to. So you are only worried about for x greater than 2. Okay, now use this property, Archimedean property, our completeness property, to establish now very important results. Now more results we are going to see. Okay, right. So the very first result is if S is a set 1 by n such that n belongs to natural number, then infimum of S is 0. So you, if you want to establish this, it's very clear that 0 is strictly less than 1 by n for all n belongs to natural number, because n cost you, and you will have this is going to be n is always a greater than 1, strictly greater than 1 number. So it's always a positive number, so it's always a positive 1 by n is always a positive. Now, so this implies 0 is a lower bound. Now we want to show that 0 is the greatest lower bound, means like infimum, right? So let t is t is greater than 0, greatest, right? So you have to choose t greater than 0. Okay, and you want to clear that t is not a lower bound. Means you are going to show that there is an element in S such which is sitting on the left of t. Okay, so let t greater than 0. So this certainly implies 1 by t is also greater than 0. Right? Since t is greater than 0, 1 by t is also greater than 0. Okay, now the Archimedean property gives you what? Archimedean property implies there exists some n, certainly depending on this number, such that 1 by t is less than equals to nt. So this will tell you that 1 by nt is less than equals to t. Since nt is in n natural number, nt is the set natural number, so it's never be 0. So you can go with the you can see this nt on the left and t on the right. So, but 1 by nt is belongs to S. What? This 1 by nt is belongs to the set S. So you are able to identify an element which is sitting on the left of it. So this implies is not a lower bound. So any strictly greater than 0 number if you start with, that is no more a lower bound. And so 0 is the greatest lower bound. So this implies 0 is the infimum of S. Okay? Right. Any doubt here?
So is infimum, but it is not included in set S.
Yes. Infimum of S is 0, but 0 is not belonging to S. So that's why I here write on S 0 strictly less than 1 by N. See, in the limiting sense, it tends to 0. That's limit. If you try to go with the limit 1 by N, it tends to 0, limiting sense. Okay. But even if this set is not closed, because limit point is not inside the set. That's also, you can, in the other words, you can see. Yes, any other question?
Sir,
Yeah.
we can say that T is a upper bound.
No.
No.
Because this is a fixed NT. You will be able to find an NT. It's not saying that for every N in N. Okay. Archimedean property will give you A and T. That's A, not all. Yeah. See for this like what you can from here, if you take any member sitting on the right of NT will satisfy this condition. But what about the left? Okay, try with it. It's not saying all. Okay, it's saying A and T. Okay, there is exist A. Okay, right.
Sir. Sir.
Yes.
I do not understand last step, but 1 over NT belongs to S.
So 1 by NT belongs to S, right? How this see the set structure here. 1 by N such that N belongs to N. So whenever you take any form of the number, this is 1 by N type. Whenever the denominator, so numerator is fixed, denominator is any natural number. So 1 by NT is also a natural number, so definitely is going to into the set S. Okay, and once you identify a number in between, you don't know whether T is covering S, means T is completely going on the upper. See, T is greater than 1 cannot be possible, because every element 1 by N is less than equals to 1. If you look at here, so you can means 1 by N is less than equals to 1 for every N in N. Right? Because N equals to 1, then it will certainly give the equality. Okay, and other members always strictly less than 1. Okay, so if you choose T is greater than 1, there's nothing to prove, because every member is sitting on the left of it. So 1 is not, and though, so T is not going to be a lower bound. Okay, because we are trying to identify, suppose T is greater than 0. If you take any number which is strictly greater than 0, if you show that this is not a lower bound, 0 is a lower bound, so 0 is the only greatest among them. Okay, so that is why this T is not a lower bound implies 0 is the greatest lower bound, which gives you that infimum of the set S is 0. Okay, right. Okay. Now let's come to the so similarly you can show that supremum of S is 1, which is inside the S. Okay, that also you can prove. Okay, that I can lift as an exercise for you. That's a very similarly you have to go with it. Okay, right. So if so the another the second property, if T greater than 0, there exists NT belongs to natural number such that this happens. Yes, this is already has been proven just now. If you look at that, it's certainly T greater than 0. This implies 1 by T. So this follows the same proof. 1 by T greater than 0. So Archimedean property gives you a NT, which satisfies this inequality, which implies the above property. And certainly this is 0 is strictly means less than 1 by NT. Okay, so the second property is holds true by following the previous one. Okay, so the third one is also follow up by the Archimedean property. Okay, so how will you establish this result? It's again, let's so here it is given that y is 0. Okay, so then Archimedean property gives you what? Archimedean property gives you an m in set of natural number that y is less than equals to m. So we don't know how far m it is giving you because there exists an m. Okay, it may be very far, it may be very near to it. Okay, but it will give you the y next natural number to it. Okay, that is at least. Okay, now what you can define. So by looking at this, you can define a set which is certainly depends on y by you collect all the possible set of elements in natural number which are such that y is okay. So Archimedean property tells you that this is certainly non-empty because of this, because you're always able to find an m such that y is strictly less than equals to m. So you take m is then m plus 1, k is equals to m plus 1. So y is strictly less than m plus 1 because m is strictly less than m plus 1. Okay, so m plus 1 belongs to here, so ey is certainly non-empty. So well-ordering property of n. So well-ordering property of n implies ey has a least element. Let's say some you can say that least element we are going to say that is ny. Okay, so this has a least element. So this may or may sitting on the may or may equals to y because y may be natural number, you don't know, right? Y may be also a natural number because y is greater than 0 only known. So as a least element, say ny. So definitely y is less than ny because of the ey structure. But y may be also a natural number, so then y becomes the least, right? So this is less than equals to ny. Okay, it has a least element. Now, if ny is a least element, then ny minus 1, what can you tell about this? Ny is a natural number which is satisfying y is strictly y less than equals to ny. So ny minus 1 is not a least element. Of ny. No, sorry, of ey. That's it. So what does this mean is this implies ny minus 1 is less than equal to y less than equals to ny. Right? So this gives you the proof of that. It is actually identify, you can say on the real line, you take any possible real number y. So you will be always identify two consecutive natural number. Okay, one of them is sitting on the left of it and one of them is sitting on the right of it. Okay, so that is this property is identity. Okay, right. Now the very interestingly, now next problem is gives you that there exists a positive real number r such that r square is 2. So we have already seen that there does not exist a rational number r such that r square is 2. So if you are able to prove that there exists a positive real number r such that R square is 2, it gives you that, but if it is not rational, it is an irrational number. That is R equals to root 2. Okay, right. So do you have any question?
Yes, sir.
Yeah.
So there ny minus 1, how it is not a least element of
Ny minus 1 is not a least element. Ny is a least element which satisfying this condition. Right? So means like have this is if I want to go on the real line. So ny is the least element. This is your ny. Then ny plus 1, ny plus 2, and so on. So the least element means the very next natural number to y. So if you make ny minus 1, it goes either, so if y is a natural number previous one or this one, so either ny minus 1, so this ny minus 1 is sitting on the left of it, or it may be sitting on the y itself, right?
So
Am I clear now?
Set like that. Yes, sir.
Okay, right. Okay. Now we
Sir.
want, yes.
Sir, n plus 1 is also not a list value, no?
Yes. N plus 1 is not a list value. Means ny plus 1, yes, is not a list element. Yes.
Okay, sir.
Not a list element.
Yes, sir.
Okay.
Yes.
Ny plus 2 and so on. Ny is the list element.
Okay, sir.
So you are means you are having the set of this like this one. Ny plus 1, ny plus 2 and so on. But where to start this ny? How will you find how will you guarantee that there is such ny exists? Because of the well-ordered property. Okay?
Yes, sir.
Right. Okay. We are now in the position to establish this result now that there exists a positive real number r such that r square is 2. So to establish this result, okay, so let's go to the next page. So we want to claim is there exists an r in R such that R is greater than 0 and R square is 2. Positive. Okay, that we want to establish now. Okay, so now let's consider the set S. So let's define the set S, set of all real numbers which are greater than 0 and x square is less than 2. Let's consider this set. Now, clearly, 1 belongs to S, 1 is greater than 0 and 1 square is less than 2. And S is a subset of R, yes, not N. And 2 is an upper of S. So S is non-empty, is a subset of real line and it has an upper bound. So then completeness property, or you can say supremum property, gives you what? Completeness property of R implies S has supremum of S exists and it exists and supremum of S is equals to so inside in R, set of real numbers. Now let you have this is supremum of S is equals to R. So to stay so R, so definitely supremum of S is equals to R means R is certainly greater than 0. Okay. Now we want to establish that R square is 2. So claim is R square is 2. So how would you establish is you just R is a real number, so there is 3 possibilities. One possibility is r square less than 2, r square equals to 2, and r square is greater than 2. So there are 3 cases. Okay, so if you strike off 2 cases, means if you prove that this does not happen, so only possibility is r square equals to 2. Okay, so we are going to make a contradiction whenever you are assuming r square less than 2 or r square greater than 2. It's no more a supremum. That's what we are going to do then. Then this certainly implies these both things cannot be true. So only the third point can be only true. Okay, right. So now let r square is less than 2. Now what we want to show now is r square is less than 2. So r is in you have r is inside S, right? R square is less than 2 because r is satisfying this in x belongs to r is greater than 0, and r square is less than 2, r is in S. Okay. Okay. Now, but r is a real number. Okay, r is a real number, r square less than 2. So r belongs to certainly S here. Okay, and r is greater than 0. That's very clear now. Now let's look at, so r square is less than 2. So I wish to, so you have, this is like if you on the real line, if you look at, let's say 2 is here and this is 0. You are trying to identify a r, so r is less than 2. Suppose r is sitting here. But if you look at the real line, it is not possible that, right, r square equals to 2. If you look at this, like what you get the intuition is there is some element here which will become the upper bound, or which will goes to this 2. There is a possibility that you will able to find there are infinitely many numbers in between this. So this will this is going to be this, right? So now what we are going to do is, let's try with r plus 1 by n whole square. Let's try with this. That's going to be r square plus 1 by n square plus 2r by n. Right? Now r square is less than 2. So this is certainly less than less than 2 plus 1 by n square plus 2r by n. So we have to use this fact that r square is strictly less than 2. Okay. See, this is r square is strictly less than 2. Okay. So further, this is going to be, as we told, 1 by n square is strictly less than 1 by n. So this is going to be r square plus 2r plus 1 by n. Okay, now what we want to show is this is strictly less than 2. Okay, that's we want to claim. There exists some n in such that. Right? Now r square is strictly less than 2, so we are going to use that. So this is only true. So we wish to find an n natural number such that this r square plus 2r plus 1 by n is strictly less than 2. This is if and only if when what will happen, 2r plus 1 by n is strictly 2 minus r square. Right? Now, so this is if and only if 1 by n is strictly less than 2 minus r square divided by 2r plus 1. Right? We wish to identify an n r square, this whole quantity is strictly less than 2. This is true if and only if this 2r plus 1 by n is strictly less than 2 minus r square. R square we are sending on this side. This is if and only 1 by n is strictly less than 2 minus r square by 2r plus 1. So whether such n exists or not, that we have to make some guarantee here. So now our goal is to establish this. So this is if and only 1 by n is less than 2 minus r square divided by 2r plus 1. Now note that r square is strictly less than 2. This implies 2 minus r square is greater than 0. Also, r is greater than 0. This implies 2r plus 1 is greater than 0. So, these two together will implies 2 minus r square divided by this 2r plus 1 number is strictly greater than 0. Now, we use the fact that we have used that if t is greater than 0, we will always able to there exist an t in n such that 0 less than 1 by nt less than t. That we have already established the result by using the Archimedean property. So Archimedean property implies there exists an n. It certainly depends on r, okay, in n, such that 1 by nr is less than 2 minus r square divided by 2r plus 2r. So such n exists. Okay, so now you go back, so you replace n by nr now. So this is true for nr. Now you go back and replace this by nr now. Everything remain same. So and this is going to be less than 2. So this whole story tells you that so thus above implies x, not x, r plus 1 by nr, which is greater than r, is so this implies this greater than r and is such that r plus 1 by nr square is less than 2. But r is supremum of S. What does that mean? R is the least element which is satisfying this. This above this implies R is not a supremum, because you have found R plus 1 by nr, which is sitting on the right an element of S. So this implies R plus 1 by nr is a supremum. So this is not possible. So which is a contradiction to the fact that R square is less than 2. Okay, contradiction to our assumption that R square is less than. This only happens because of this. So this our assumption is wrong. So this implies R square is greater than or equal to 2. That's only the possibilities.
Sir,
Now
upper bound, or we have also contradicted that R is not also an upper bound.
yes, R is not a supremum means see R square, R is certainly is a member of S, and R is not a supremum. Then R is not a supremum, right? Because R is an element of S, so the supremum may or may not be inside S. So, but here, if you assume that R square is less than 2, means it's an element of S only. Did you
Okay,
get
whether it is upper bound or not? I'm asking, sir. Now,
No, it's not, right? Because you have identified another element, no, of S, which is sitting on the on the right of it, right?
but sir, yesterday we have found that if U is upper bound and we can have more than one upper bound, U plus one, U plus two, and our supremum would be U itself, which is the least upper bound. So here
Yeah. Huh.
R is itself an upper bound, then R plus something would be also upper bound, but not supremum.
Correct.
Then
Oh, correct. But here the problem is happening is because of the structure of the set S. Okay, the S structure, if you look at here, so the structure of S, if you look at, it contains all the elements x greater than 0 and x square is less than 2. So whenever you are able to find an x, which is such that x square is less than 2 and x is 0, it's inside S. So you have R plus 1 by n R is also inside S and R is also inside S. Because of this R square less than 2, if you start with, R is inside S and R plus 1 by n R is also inside S. So but R is strictly less than R plus 1 by n R.
yeah.
So you are able to identify an element in S which is sitting on the left, on the right of it. So it cannot be no more upper bound, right?
So there must be only one upper bound in one set.
Yes.
Oh, okay, yeah.
Okay, inside the set, if it is an upper bound, it's a least upper bound and it is only one. A supremum, whenever it exists, it is unique. It also can be true.
Okay, that's right.
Okay.
Yeah, sir.
Right. So I think, is there any problem in following the proof?
Sir, go one slide back.
Yeah.
Yeah, in this, I did not understand the step from blue ink to red ink.
Yeah, this here.
Yes.
Okay, so this is fine.
Yes, blue
This
blue
is
ink is
into
fine.
open
Then
up
first
this.
red
Okay.
is, I did not understand the first red ink.
Here, right? From here.
Yes.
Okay, so if you open up this a plus b whole square, it is opening a square plus b square plus 2ab. Okay, now 1 by n square, you use the fact that 1 by n square is less than 1 by n, less than equal to less than. So, okay, so r square plus this is going to be 2r plus 1 by r by n, right?
But sir, if we take, acha, okay, you took, okay, sir, understand. I understood.
Okay.
Yes.
Now what we want is this element is such that it is completely strictly less than 2. Okay, so now we wish to find an n. So this inequality should be true that we wish to claim here. Okay, so this inequality now hold true for some n. There should at least one n satisfying this. Then we are through. But now if you look at here, so this inequality only does hold if and only this happens. You send r square on the right. Then you note that r square is less than 2. So 2 minus r square is greater than 0. Now 2r plus 1 is also greater than 0. So you can send this 2r plus 1 on the right now. So 1 by n less than 2 minus r square by 2r plus 1. So whether such n exists or not, that is a question now. But that is given by the guarantee that Archimedean property gives you guarantee, because since this is a positive number. This is a positive number. So you are always able to identify an n such that this has been satisfied. So you are going in the right track now. So means that such n we are saying that is depending on r. So that's why it's nr. Okay. So 1 by nr is less than this. So you are just replacing by this. Then this inequality is true for such nr. So which says that you have identified an element in S which is sitting on the right of the upper bound. So this says that R is not supremum is no more, that R is not a supremum. Okay, so but that R is a supremum. Okay, so your assumption that R is less than 2 is not correct. So that is not possible. So only possibility is now R square is greater than equals to 2. Okay, so similarly, you can now lead for that r square greater than 2 also you can strike the possibility. Okay, so so you are going to have r square is greater than 2, then so if then find k in n such that r minus 1 by k whole square is greater than 2. So this is if and only if I for some steps r square plus 1 by k square minus 2r by k greater than 2, if and only if. So r square minus 2 is positive, so 2 is sending in this side, so r square minus 2 is greater than 2r by k minus 1 by k square. Okay, now see, r is certainly greater than 1. Okay, r is certainly greater than 1. R cannot be less than 1. That's also very much clear. So 1 by k square is less than 1 by k. So minus 1 by k square is greater than minus 1 by k. So this is greater than 2r minus 1 by k. Okay, so this is if and only if r square minus 2 by 2r minus 1 greater than 1 by k. And then Archimedean property gives you guarantee that this exists, because 2r minus 1 is always a positive number. This is also a positive number. So you are able to identify such k. That satisfies this. Okay. So this assumption also tells you that, but r minus 1 by k is sitting left of this. So r is not a least upper bound then. Then r minus 1 by k is the least, you can say. Okay, so therefore it contradicts the fact that r is a supremum because of this our assumption that r square greater than 2. So this is also not possible. So only possibility is r square equals to 2. Okay, right. Okay, so the you can say very last result of this session is this is also known as density theorem. Okay, it's also this fifth result is also known as famous with like density theorem. If you are aware about this density word, like dense, so set of rational numbers is dense in R. Means you take any two real numbers, between them you are able to find infinitely many irrational numbers. Okay, so between any two real numbers there are infinitely many rational numbers. By the help of this, you can also show that between any two real numbers, there are infinitely many irrational numbers there. Okay, so the proof of this also is will take the help of this so-called Archimedean property. Okay, so here if x and y are any real numbers with x less than y, then you are able to then you have to establish the following result. So I'm just writing it down. So our claim is for x comma y belongs to R with x less than y, there exists a rational number such that x less than R less than y. So the very first thing is, without loss of generality, we may assume that that 0 less than x less than y means both are positive real numbers. If they are not, means both are, then you can multiply by minus and you can still work with the similar result, and then at the end you can multiply by minus. Okay, but if suppose x is negative and y is positive, suppose it happens, then 0 is in between, then 0 is a rational number, so there is nothing to prove for that. So without loss of generality, we may assume that 0 less than x less than y. Now x less than y implies y minus x is greater than 0, then Archimedean property says that there exists an n natural number that y minus x is greater than 1 by n. This implies ny minus nx is greater than 1. This implies nx plus 1 is less than n. Now, note that n is greater than 1, right? Greater than equals to 1, and x is greater than 0. So n into x is also greater than 0. Okay, so this implies that you will able to identify. So this implies there exists an k. There exists an k in a natural number such that m minus 1 less k minus 1 less than equals to nx less than equals to k. So that we have used the last result, right? Ny minus 1 is less than equals to y less than equals to ny. Now this implies k is less than equals to nx plus 1, right? K minus 1 is less than equals to nx, so k is less than equals to nx plus 1, which is less than ny, and k is greater than equals to nx. So this implies nx is less than equals to k less than equals to ny. So this implies x is less than equals to k by n less than equals to y. So k by n is a irrational number, right? K is a natural number, n is a natural number. So if you take this as a rational form, k by n give you the rational number, and k by n is belongs to second.